In this video, we're going to begin our study of gravity, and specifically we'll look at the universal law of gravitation. Let's think about what we know about gravity so far. Well, we know how to calculate the force of gravity on an object of mass m. We know that we just take the acceleration due to gravity and multiply the mass by it. I want to remind you how we got that, because we didn't get it because we had some great understanding of gravity. What we did was we said, if I take an object of mass m and I drop it near the surface of the Earth, what we find experimentally is that the acceleration of that object is going to be negative g, or negative 9.8 meters per second squared. Well, what we then did was we said, okay, we know that the only force acting is the force of gravity, and therefore we can use Newton's second law to try to figure out how to be able to calculate that force of gravity. So the net force in the y direction is ma(y). The only force acting is negative fg. We know experimentally that the acceleration is negative g, and you'll notice that that's where we came up with the idea that we could calculate the force of gravity by just taking the mass and multiplying by little g. So that's how we got it, but obviously that's not going to be generally true. In other words, it's great to use that to figure out the force of gravity on an object near the surface of the Earth. We can even use it to figure out the force of gravity on the surface of another planet if we put in the correct value of g for that planet. But if we want to know something like what is the force that the sun exerts on the Earth, well, we can't use that formula to do it. We need to understand gravity better in order to be able to do that problem. I want to go through a couple questions just to get you thinking about gravity. So why do the astronauts orbiting the Earth in the International Space Station experience weightlessness? What do you think? So if you haven't had a physics course before, then typically what students will answer is that it's because the astronauts are very far away, and so the force of gravity is much, much less. It turns out, though, that that's actually not the case. And I want to just bring up some numbers here to kind of illustrate this for you. It turns out that the radius of the Earth is about 4,000 miles. So if we've got a person and they are on the surface of the Earth, they are about 4,000 miles away from the center. Now it turns out that for gravity what matters is the distance between the centers of the objects. Well, our astronaut who's orbiting up in the International Space Station, you'll notice they're not really much farther away from the center of the Earth than you and I are. So they're 4,200 miles away versus 4,000 miles away. Therefore, it turns out the force of gravity up where the space station is not appreciably less than it is here on the surface of the Earth. So that's not why the astronauts experience weightlessness. Another question, how do we know the mass of the sun and the planets? Well, obviously if you open up any physics textbook or you Google it, you can look up all that information. But the question is, where did that information come from? Because obviously we can't directly measure the mass of the sun or the mass of the planets. Well, it turns out that once we understand Newton's law of universal gravitation, we're going to be able to understand the answers to these questions. So let's introduce Newton's law of universal gravitation. Remember that Newton had done many other things. Newton co-invented calculus. He came up with his 3 laws of motion. But perhaps this is one of the biggest things that he did, and that was he realized that the way that gravity works on the Earth could be extended outward up to the stars. So really before Newton's time, no one that we know of had made the connection between objects falling near the surface of the Earth and how objects moved in space. So for example, the motion of the planets around the sun. Now, you may have heard the story of Newton sitting under an apple tree and getting hit in the head with an apple, and that somehow caused him to come up with this idea. Well, that may or may not have happened, but the thinking behind that story is that Newton looked up and realized if gravity works right at the surface of the Earth, but it also works up at the top of the tree, why would it ever stop? In other words, maybe it's gravity that's keeping the moon orbiting the Earth or the Earth orbiting the sun. So that's kind of the concept that he came up with that nobody else had before. Now, before we look at the law of universal gravitation in detail, I want to mention that at Newton's time, the rules of planetary motion were already known. So Kepler had developed 3 laws of planetary motion, but he had done it just based on observations of where the planets are night after night in the sky. He didn't understand why he got these 3 laws of planetary motion. He just found that he was able to come up with 3 laws that matched the data. But once Newton developed his theory of gravity, then he could actually derive Kepler's laws. And so we will see Kepler's 3 laws of planetary motion in the next video, and we'll actually go ahead and see how we can derive them from Newton's universal gravitation. So here is the law of universal gravitation. First of all, it says every object in the universe attracts every other object in the universe. So that's important. It's not just that the Earth exerts a force of gravity on you. Every object in the room that you're sitting in right now is also exerting a force of gravity on you. And in fact, every object in the universe is exerting a force of gravity on you right now. The force of gravity is always attractive, so it's never repulsive. It's always attractive. And Newton was able to determine that the force is equal to big G, which is a constant, not the same as little g, times the mass of the 2 objects divided by the distance between them squared. That distance, r, is the distance between the centers. Sometimes students get confused with that r, because when you see r you think radius, but it's just the distance between the centers. Now, when it's something like the moon orbiting the Earth, you'll notice that that distance between the centers is the radius of the moon's orbit. So it can be radius, but really it's just the distance between the centers. Okay, so we call big G the gravitational constant. What do you think? Is big G a big number or a small number? And how can you figure that out? Well, the answer is that G is a really small number. And here's how you could reason that out on your own. Let's say that I take a 1 kilogram object and another 1 kilogram object, and I separate the 2 objects by a distance of 1 meter. So you'll notice that m1, m2 over r squared would just be 1. The thing is, if you have 2 objects that are near each other, 2 small objects, do you notice an attraction between them? When you're walking next to the wall, does the wall feel like it's going to suck you in? And the answer is no. We don't notice the force of gravity at all when we're just looking at interactions between everyday objects. So G has to be really small so that would explain why we don't notice the force of gravity unless one of the masses is really big. Here's a question. Does the sun exert a greater force on the Earth than the Earth exerts on the sun? Pause the video and think about that for a moment, and then restart. Okay, hopefully you all yelled no. Because, after all, one of the most important things we've learned in this course is Newton's third law. Newton's third law always applies. Remember, Newton's third law says that object A exerts a force on object B exerts an equal and opposite force on object A. So if I write out the force that the sun exerts on the Earth as FSE, then the force the Earth exerts on the sun would be FES, and we know that in magnitude those forces have to be the same. So opposite direction magnitudes are the same, or FES is equal to FSE. Now the other way you could have thought about this logically is just that there's only one law of universal gravitation. In other words, we only have one formula. Whether I'm calculating the magnitude of the force that the Earth exerts on the sun or the magnitude of the force the sun exerts on the Earth, we're going to use the universal law of gravitation. So big G, mass of the Earth, mass of the sun, divided by the distance between their centers squared. So there's only one formula to calculate either of those forces, so they better be the same. Why don't you go ahead and pause the video after I read this question and calculate it yourself just to make sure that you get the right answer. It says, what's the gravitational force between two people, one with a mass of 70 kilograms and one with a mass of 80 kilograms, separated by a distance of half a meter? In other words, if we were in class together and two students were sitting next to each other, this would be the force that one of them exerts on the other due to gravity. To calculate it, I'm just going to use the universal law of gravitation. So I've got G m1, m2 divided by the distance between them squared. G is 6.67 times 10 to the negative 11th. The mass of our first person is 70 kilograms. The mass of our second person was 80 kilograms. And I'm dividing by the distance between them, which is 0.5. And I've got to make sure to square that. So when I calculate that, what I get is 1.5 times 10 to the negative 6th newtons. You'll notice that is a very small force. Just to show you how small a force that is, let's say that you take your hand, this is your hand, and you put a paper clip on your hand. What force is that paper clip exerting on you? Well, you may remember when you learned about the metric system way back when that the mass of a paper clip is about 1 gram, or 0.001 kilograms. So the weight, or force of gravity, of a paper clip is 0.0098 newtons, or roughly 1 times 10 to the negative 2 newtons. So when that paper clip is sitting on your hand, you can hardly feel it. And notice that this is a much smaller number than that. And that's why in our everyday lives, the only force of gravity we notice is the force of gravity that the Earth exerts on us. Because since G is so small, one of the masses has to be very, very big to notice a force of gravity. So we said that big G is not the same as little g, but it turns out that they are related. And let's see if we can figure this out. Notice we actually have two different ways now to figure out the force of gravity for an object near the surface of the Earth. So here's the Earth. So we got the mass of the Earth. And let's take an object somewhere near the surface of the Earth, near enough that we can say that the object is a distance away from the Earth just equal to the radius of the Earth. Well, one of the ways we can calculate the force of gravity is the way we've been doing it all semester, that it's just m times the acceleration due to gravity. But we also can now calculate the force of gravity by using the law of universal gravitation, which would tell us to use big G times the mass of the Earth times the mass of the object divided by the distance between them squared, which in this case is just the radius of the Earth. Well, these two formulas have to give us the same result. In other words, mg has to be equal to big G, mass of the Earth, m, over the radius of the Earth squared. And you'll notice that the mass of the object cancels out, and we get that the acceleration due to gravity is just big G times the mass of the Earth divided by the radius of the Earth squared. Now, with that formula, we could now calculate the acceleration due to gravity on the surface of any planet just by replacing the mass of the Earth with the mass of the planet and the radius of the Earth with the radius of the planet. We also now can see why little g is the same for any object, because fundamentally the acceleration due to gravity is just related to the gravitational constant, the mass, and the radius of the planet that you're on. Let's talk more about this idea of weightlessness in space. I want to remind you of a problem that we looked at earlier in the course, which was somebody riding in an elevator. If you remember, our person is in the elevator, they're standing on a scale. If we draw the free body diagram for the person, there are only two forces acting. There is the normal force that the scale is exerting up on the person, and then there is the force of gravity. Remember that the normal force, the force that the scale exerts on the person, that actually is the scale reading, because of course the person exerts an equal and opposite force down on the scale. When we analyzed this before, we used Newton's second law. We said the net force in the y direction is equal to ma(y), and therefore the normal force minus mg is equal to ma(y), or the scale reading, in other words Fn, is equal to mg plus ma(y). And then we went through some different examples of that, but I want to look at what happens if we just cut the cord when the elevator is at the top of the building. Well, we know in that case that the acceleration of the elevator is just going to be equal to negative g. So notice what happens to our weight. We get mg plus m times negative g. In other words, our weight goes to 0. And so that person in the falling elevator is experiencing weightlessness. Again, if they take something out of their pocket and let it go right in front of their face, it's just going to appear to float there. Now really, the two objects, the person and whatever they let go of in front of their face, are both falling at the same rate. But if you're inside the elevator, everything will appear to float. So we call that apparent weightlessness. It's not that there's no force of gravity. It's not like the force of gravity on you is 0, but everything is in free fall together, and so it feels like there's no gravity acting on you. Now obviously, we don't want to have to experience weightlessness by being in a falling elevator, but it turns out that there's a much more clever and safer way to experience weightlessness. Let's look at how Newton thought about it. This is actually Newton's own drawing, and it was his thought experiment about orbits. And here's what he was thinking about. He said, if I shoot something horizontally near the surface of a planet like the Earth, we know what it's going to do. The object is going to go through projectile motion and come down and hit the surface. However, if I can fire this object fast enough, then the curvature of the planet becomes important. And there is a speed with which I fire it, so that even though the object is continually falling towards the planet, it never gets there. And that's the whole idea of an orbit. So when something like the moon or an artificial satellite or the International Space Station, are orbiting the Earth, the important thing to understand is they're constantly in free fall. They're constantly falling towards the Earth. But because of that initial horizontal, or I should say tangential velocity, the object will never get to the Earth. So that's what's happening for our astronauts up in the International Space Station or in any rocket that's in orbit around the Earth, is that they and everything inside the rocket and the rocket itself are constantly falling towards the Earth, but they have enough tangential velocity that they will never get there. So for the ISS and everything in it, it's constantly accelerating towards the Earth in free fall. Notice that if we look at the case of a circular orbit, this is just uniform circular motion. And so in fact, if we want to figure out how much velocity do I have to give the International Space Station so that it won't crash down into the Earth, we can actually figure that out pretty easily. We know that the net force has to be equal to the mass times the acceleration. And since this is a case of uniform circular motion, the acceleration is v squared over r. Let's draw in a few more things here. So again, the distance that matters is the distance from the center of the Earth to where the International Space Station is. And of course, the mass of the Earth matters as well. Well, the force of gravity acting on the International Space Station is just going to be the law of universal gravitation. So g times the mass of the Earth times the mass of the space station. And that's got to be equal, or sorry, divided by the distance between them, r squared. And that's got to be equal to the mass of the International Space Station times its acceleration around the Earth, which would just be v squared over r. Notice that the mass of the International Space Station cancels out. I can cancel the square with the r down here, and I find that v is equal to g times the mass of the Earth over r. So here we are literally doing rocket science. That's the velocity, that's the tangential velocity that I've got to give the International Space Station for it to stay in orbit a distance r from the center of the Earth. In our next video, we'll look more at the idea of orbits and we'll cover Kepler's laws of planetary motion.